So I want to make a few small remarks about the doubled Lie. I won't go into a lot of detail with this. I do suggest that you see the Rushworth paper. And you'll recall that last time we talked about the strategy for defining this and about the Lie homology that's related to it, and how the differentials, the algebra works for the Lie homology. And maybe I should recall that for you a little bit so that the remarks I'm going to make will be sensible. So let's take a look at the notes from the previous lecture. Just a second. So certainly is an interesting strategy, and it's probably worth just reviewing it so that we have the context. What Rushworth does is he's going to find another way to solve the problem, which I recalled for you, of if you use the usual Khovanov homology algebra, the usual Frobenius algebra, and you consider this problem square here, then you have single cycle maps going around the square this way. And in our original situation, we would take these maps to be 0, but then you would have m composed with delta, and that would give you 2x if you started with a 1 up on here. And so that tells you an important point, which is that Khovanov homology extends with no pain as long as you're on mod 2. And that leads to some interesting questions, some of which may not have been fully tracked down yet by us, such as what happens to the Lie homology and the Rasmussen invariant if we're going to try doing this mod 2. I'm not quite sure I know the answer to that. And in any case, it's a good idea to go over the integers, but to go over the integers requires solving a problem. And we talked about how we had solved it using Monturov's method. And then last week, I told you about Rushworth's method, which is very interesting. Namely, he's going to associate two modules, an upper one and the lower one, to every state. So when you look at a state circle, there are really two state circles. Not only are there the ones labeled, there were before, there was a state circle labeled by X and a state circle labeled by 1. And those were the generators of the module associated with the state circle. But now we're going to have an upper and a lower module, 2 modules, which means 4 elements that could basically label that circle. A 1 upper L, a 1 lower, a 1 upper U, an X upper U, and an X upper L. And these algebras behave, the upper algebra behaves just like the original algebra, the lower algebra behaves just like the original algebra, but now the single cycle map acts as a kind of an exchange course to move upper and lower to each other and back. And in particular, in the straight Khovanov algebra situation, 1 upper goes to 1 lower, X upper goes to X lower, 1 lower goes to 2X upper, and X lower goes to 0. And if you look to see what happens in the problem square, you realize that this method of defining the eta solves the problem. The eta is no longer 0. When you compose eta with eta on 1 upper L, for example, you get 2X upper mu. That's the rule. 1 upper L goes to 2X upper mu, and then X upper mu goes to X upper L. And so you go, X upper U. I'm misreading my own notes. Yes. We had 1 upper L, which goes to 2X upper U. and x upper u goes to x upper L under eta again. So I should have 2x upper L here, and I've miswritten something. When I started with yes, of course. I meant to write a U here instead of a, sorry, I'll fix that and send another version of these slides. But I mixed up U and L when I was working here. About perhaps not in the inner slide. Yes, in the inner one, I'm doing the other one. So it depends on which one you're looking at. But if you look here, upper U goes to 1 upper L, and 1 upper L goes to 2x upper U. And if you go around the other way doing delta, you don't change U. You got 1x, 1 tensor x, x tensor 1, and then you multiply. So it goes in and back out and ends up commutes correctly. And so that works and gives you the correct behavior on the problem square, and thereby generalizes the homology in that way. And indeed, you can check that this homology has the correct invariances under the Reiner-Meister moves as before. I think that you will find when you read Rushworth's paper that he is extremely concise but correct about everything he says. So you'll have an interesting time, a kind of beyond the course exercise to work with Rushworth's paper and check various things. And then there's the matter of the Lie algebra. We go to the Lie algebra before by changing the Khovanov algebra in this way, so that delta of x was x tensor x plus 1 tensor 1. And I do recommend that you go all the way back to the beginning of our analysis of how the algebra works in relation to the cobordisms to see where this came from. But then what will Rushworth do here? Well, he'll do the same thing he did before. He'll keep those definitions, and we'll find that the Lie algebra accepts them in the same way. And so what we end up with is, in the old Lie algebra format, we have this nice collection of relations, that if we let R be 1 plus x over 2 and G be 1 minus x over 2, then we get the Frobenius algebra description over here like this. And then we find also that if you apply the single cycle map to these, then R goes to L, G goes to RU goes to RL, GU goes to GL, RL goes to 2RU, and GL goes to minus 2G mu. And then you can follow out on the problem square there and see how it works. For example, here I'm running through the problem square on RU, which under eta goes to RL, and under eta, again, RL goes to 2 R mu. And so by factoring it in that way, you end up with the doubling that you wanted, because R mu under delta goes to 2 R mu tensor R mu, and R tensor R times R is R. And so we get the commuting that we want. And so we get Khovanov homology over the integers in this way by doing a clever factorization in the algebra. And it's going to be interesting when we finally get all computer programs available. By now, I should report to you, and perhaps I will report to you in a little more detail next week. I have Mathematica programming available on regular virtual Khovanov homology now. We're almost sure that it's working, so I could send it over to you next week. I'll know whether it's really working, or we'll be pretty sure. And you can try it out if you have Mathematica. That's for the Monturov type version. And we're going to want a program for this, and we're going to want to be able to compare the two homologies. So there will be calculations that one can play with. I left it as an exercise for you to check that eta behaves this way on the R's and the G's. And since I'm supposed to hand you a problem set to do, this exercise is going to be on the problem set. You can bank on it. Okay. Then there is the matter of the coloring. And this is quite interesting. And I want to talk about it a little bit now. So let's go over to my other slideshow where I can draw you some pictures. So you'll recall that we are now going to talk about red, green coloring of states. And we're going to get them by taking red-green coloring of the diagram. So I might take a, pen is behaving strangely. We might take a simple virtual diagram like this. And we are going to do alternate red-green coloring. So this is a simple bit of combinatorics. I just color this red, and then when I make a crossing, I color it green, and then red. And across a virtual no change, and green, and red. And then you see that there is the possibility of smoothing the diagram to get a colored state in this fashion. So if you were doing it with this diagram, we would end up with this state. Colored red here and green here. And you will notice that since red times green equals 0, and of course we can color upper or lower. And the way I will color, if I'm doing that, which I won't write, would be, for example, R upper, green upper, and then maybe R upper here and green upper. I would keep it all colored in the same algebra like that. And then we can break it into a state like this. And the point is that that boundary will take this to 0. Because at every juncture, you're going to have two distinct cycles, and red times green is equal to 0. So it breaks up and automatically gives you a cycle. And then you, in fact, do get a theorem. And there's a little more work associated with that, and I refer you to Rushworth for that. That the rank of the doubled Khovanov homology Lie, prime means Lie, of a given link L is equal to twice, because of the doubling, the number of alternating color smoothings of the diagram. The difference between what happens here and what happened in the original situation is where these smoothings occur. For example, if this knot had been our old friend, the positive virtual trefoil, then you see that the smoothings that land on that coloring are the coloring comes from smoothings which are not the A smoothings, nor are they the Seifert smoothings. So these are often not Seifert. And that means that the kind of conclusions that we were able to draw before about Seifert states in relation to elements in cohomology are not available anymore from the Lie homology, but still invariants and Rasmussen kind of invariants still are available by comparing how these cycles work with how they work in the Khovanov homology. You still get a lot of cycles. They are located in different places, and they are not boundaries. That's what this theorem is telling you. And so it provides a very nice framework out of which to understand what's going on with the link in relation to its Khovanov homology bubble. And so there's certainly lots more to understand there. And if we were continuing this, we would be wanting to continue it as a kind of a seminar rather than a course, I'm convinced, where you or whoever was working on this would alternate and choose bits of Rushworth's paper and some other papers and report on them. That's the way we ought to go and continue this. And in fact, it is possible to continue in this way in some of the other seminars that we are working with. We'll continue to talk about these matters in the seminar with Roger Fenn and also in our quantum topology seminar. So I encourage you to look at Rushworth's paper and keep thinking about this. Now let's talk about some other thoughts related to this. The doubled Khovanov prime of a link L categorifies, this is the Lie, categorifies the binary bracket. That's a statement that you might want to try unfolding in detail, but you can see the outline of that quite clearly, because remember that the binary, all right, binary bracket of K, for the sake of writing something for that, the binary bracket of K, maybe we'll write it as curly bracket of K, all right? The binary bracket of K has the property that it is equal to the sum over, we could call them the RG colorings of L. And then for each RG coloring, let's call it sigma, we have L sigma, where L sigma is equal to product of A or A inverse according to the smoothing. We talked about this before, but you see, this is an invariant which is running over exactly those colorings. So for example, if we were talking about this knot here, then you would consider a smoothing like this one. And that tells you should be coloring, and then you have to look at this smoothing. So in this case, that's the smoothing that contributes. It's not a big contribution. You could also flip to green and you'll get two of these. And then for each one, you will get the product of the A's and the B's. In this case, you get an A inverse and you get an A inverse. So you get an A to the -2. And then you get two of them because of the fact that there are two colorings. And so it shouldn't be surprising that this is underlying the homology that we're talking about, the same generators as this invariant. So this leads to the following question, which I'm only going to speculate about here. What about homology in relation to non-topological generalizations of binary bracket. Now, what I mean by that is the following. I'll give you an example. I have a feeling. I think I erased something I didn't want to erase, but no matter. Yeah. We can consider I'll give you an example that I'm interested in. Red, green, and blue, 3 colors. And we can consider a binary bracket on diagrams, which is defined by, let's just put some variables in here. We'll have an A. And this means colored differently on B. And this means colored differently, right? And the value of the loop will probably be 3 for my purposes in this case, since there are 3 ways to color a blank loop. And this means colored differently. And then you will find that that's an interesting kind of graph theoretic polynomial to consider for knot diagrams, but it will not be not invariant under Reidemeister moves, not topological. But on the other hand, coloring that way looks like this, of course. You have crossings, and you might have red and then green, and you might have blue, and I'm sorry, you might have red and green and red. So you're going to want something like that. But you could also have red and blue and blue just as well. All right. You can have any pair. At every crossing, you're going to see a pair of colors, and it will switch, and it will have to be the same switched pair, but you will not see. But you can see different colors. And this corresponds, as we have discussed before, to going over to a graph situation where you have red and green coming in, and then there is a graphical edge in here. And that graphical edge would be colored by the 3rd color. So you'd have green, red, and then you'd have a blue in here, and then you'd have green, red, like that. And you can think of calculations involving a link as corresponding to calculations involving a graph, possibly by adding some virtual crossings, as we discussed before. And over here, it would be, again, a graphical edge, and then you would have red and blue, and you'd have a green in here. And then you see that what the polynomial that you are computing here when you are working in the not diagrammatic category, possibly virtual, what you are computing here is counting the possibilities of three colorings for the underlying graphs, some of which are planar and some of which are not. So this polynomial is useful for studying three colorings of trivalent graphs. And we can make this more precise, and we did. So I just want to remind you in what way we did. At graph level, we could define the polynomial at a marked or perfect matching edge like that is going to be equal to the polynomial. It would be multiplied by a for these purposes. A polynomial where I split it this way and ask that these be colored differently. We're using three colors. Plus b times the polynomial where you cross-connect it and color it differently like that. And you can think of that as a virtual crossing. I think I prefer to think of that cross connection, put this symbol over there on the other side just for my own purposes. Yes. All right. So, no, it doesn't really matter. So you see that if I, and this is actually the a polynomial which is running over the different ways of possibly three coloring the trivalent graph, because when you three color the trivalent graph, you run into the following two basic cases, which I'm just reminding you so you see how this ideas work. You might have red and green, and then this would be blue because you want to have three colors, different colors at a vertex. And then it might be that this comes out red and that comes out green. Or you might have red and green coming here and blue here, all right, but then you have red here and you have green here. And you see that if you were to fold this up like this, red, red, green, green, and think of that as corresponding to a state like this, then it would be a smoothing like that. And if you were to do it in the other case, you would have it flipped on the other side. So that isn't going to work. So in order to carry this over into knot theory, what we do is we take this guy and we send him over to, this is the basic idea, we send him over to a crossing followed by a virtual crossing to get rid of the switching. And then you will see, this didn't work right, then you will see that everything works just fine, because what happens to this one, let's call this one 1 and this one 2, and examine what happens to 1 and 2 when you make this association, which we call K, taking graphs to virtual diagrams. So then let's see what happens to our formula. Our formula will then read, or if we want just crossings, you see, another way to put it is, sorry, I want to put it the other way, but let's do it this way. All right. So then if we translated it, it would look like this. We replace the graphical bit by this, and that is supposed to be equal to A times P times this is different from this, and there's a little virtual crossing, plus a B times this, and now there is you'll excuse me. I wanted to be completely literal about my translation. And to be completely literal about my translation, I only take this one over, and these are already, if there's nothing there to translate. So this is going to be the same as it was before. I'll write it like that. All right. But now if you were to multiply this equation along the bottom by a virtual crossing, you will get that this is equal to A times multiplied on the bottom by a virtual crossing doesn't do anything to that. It stays exactly the same. But the other one multiplied on the bottom by a virtual crossing becomes the smoothing in the other direction. This one. And so you see, that's the bracket expansion that we were talking about before. So a bracket expansion, which isn't topologically invariant, corresponds to a coloring polynomial for calculating a perfect matching polynomial that runs over all the possible colorings. And then you can specialize this to actually count the colorings. And you can do a lot about trivalent graph colorings. But over in the virtual knot category, it corresponds to a polynomial which is not topologically invariant. So this is a graph polynomial in the virtual knot category. So now that you understand what polynomial I have in mind, I can ask my question, which is a research question. So the question is, consider the polynomial we were just talking about. And even maybe have another, well, we'll make it 3, and we're going to use RGB just to be specific. But we could have many, many more colorings and the same rules, right? Consider that. Is there a natural categorification of it? Is there an RGB algebra that would be natural to use, as we have been using? And of course, this is in virtuals. So we would want to generalize the Lie homology. And we aren't insisting that this homology be invariant under Reidemeister moves. It's a graphical homology that would be possibly defined. So the constraints on us to invent this are considerably less than making Khovanov homology. We are only looking for a combinatorial framework in which there would be homology. And of course, and if we had it, could it be used to study graph colorings. So I'm going to take it as a bit of homework for myself, you might think about it, to see whether I could generalize the Lie algebra to an RGB algebra that would give me a homology theory. I don't insist on topological invariance. I'm just looking for a way to reflect the coloring problem into a homology theory in a creative way. So you see, you can ask a lot of questions. You could make up other questions. And of course, you may find yourself making up questions and going down pathways and giving them up, or you may find that you go down a pathway and find something very interesting. There are a lot of things that are possible here. So that's what I wanted to say about the Lie homology and the double Khovanov homology. Now, I want to go to another part of, let me save that. I want to go to another part of the discussion that we were having. These are the FKT formal knot theory states, or marker states, and we were talking about them and how they could be used for some generalizations. And I wanted to tell you how these states come up in the knot floor homology. They are related to knot floor homology. And I won't go into the theory of knot floor homology, but I'm going to give you a little sketch. And I will give you some papers that you can read if you're interested. But this is combinatorics, which ends up being related to this. And there are, again, questions, some of which seem hard, other of which are partly worked out by people about the relationship between these states and the knot floor homology. But in order to do that, and you'll recall, maybe you should recall last week what I was talking about, if I still have it up here. We talked about the coloring a bit. And then we talked about the marker states. And I'll go back and talk about this from the beginning, but we talked about them, and I told you a little about them and how they work, and how they are related to the Conway polynomial, and a little more about that and how they're related to knotoids. And I think I want to go back and tell you that story again. I may use some of these illustrations since they're useful, but I want to tell you the story of where these states come from. And then I'm going to also tell you another story about how they're related to the knot floor homology and how some attempts have been made to relate them more deeply to the knot floor homology. You'll see. But let's go back all the way back now. And I want to tell you about the paper of J.W. Alexander in 1928 in the Transactions of the American Mathematical Society, in which he produced the Alexander Polynomial. Which is denoted by delta k of t for a knot or link k. I'm going to show you the definition that he used and show you how these states are related to that definition, a way of thinking about that definition. So what Alexander did was the following. He has a notation. I'll begin with this notation. He has a dot notation like this. You could use this notation to tell that this is an undercrossing if you wanted to, so you wouldn't even have to draw the undercrossing. When you have an oriented line and two dots on the left of it, it means that it goes underneath. But then the associate, and then these are the regions. These are names of the regions. A, B, C, D, and so on are region labels. All right. And then we're going to we'll construct a module with region generators. That is, each label for a region is a generator of the module. And one relation per crossing. And it will be a module over the ring Z T T inverse. Now, if you're familiar with modern knot theory, then you know that the so-called Alexander module is constructed as a module with some generators over the ring ZTT inverse. Where it happens that these are region labels, I will remark in a moment, but that's what he did. He used region labels. And the relation that this corresponds to is TA minus TB plus C minus D. So that means that this bit of algebra is set equal to 0, and you're looking at Z of A, B, C, D, etc., and also T and T inverse, modulo the relations. So you're setting this equal to 0. You're saying that T times A minus B is equal to D minus C. And we're going to get a polynomial out of that. How? Oh, just keep that. I should remark that regions correspond to using the Dane presentation of the fundamental group of R3 minus the knot. In the Dane presentation, one thinks of the knot as in a plane in R3 like that. And you have a base point, which is perhaps far above the plane here. And then a generator of the fundamental group consists of going down from the base point, piercing this plane, continuing down underneath, and then coming back up through one of the regions and back to base point. And if this region here, if this region was labeled R, name of region, then this element in the fundamental group would be called R. So there is one generator in the fundamental group for each region in the knot diagram, and the outer region is the identity in the fundamental group. And then you get a relation in the group at each crossing of this kind. If these were the fundamental group generators, it would be A, D inverse, C, D inverse equals 1. And these are these are reflections of that, but I won't describe it any further. But they are kind of reflections of that. But what Alexander did was he explains, as you'll see in a moment, not anything about the fundamental group except in remarks at the end of the paper, but rather he explains how to write down the relations for the module, and then he describes how to write down a relation matrix for the module, and then he describes how to extract from the relation matrix a polynomial by taking a certain determinant. It becomes very concrete. And then he shows that this determinant is invariant under the Alexander-Briggs-Reidemeister rules. And so you have the polynomial invariant. And we're going to see the combinatorics of this. So what will this look like if we were going to actually work with a given knot? I will transfer to another page in a moment, but let's just use this space. I might have a trefoil knot here. I might have regions A, B, C, D, E. And then I have a relation at each crossing. There's a double dot here. There's a double dot there. And there's a double dot here. And from this, I can read the three relations. And then I'm going to make a matrix out of those three relations. But we need a little more space for that. The reason I'm going through this is because this is an interesting algorithm for calculating the Alexander polynomial, and you're going to see those states come out. So here we are. And let's call this crossing 1, and this one 2, and that one 3, and write down the relations for each. So at 1, I have TA minus TC plus E minus B. At 2, let's see, TA, TC, TACEB, ACEB, right. Next one is ABED. And the next one is ADEC. Check that. ADEC, ABED, and ACEB. Okay, so now we write down a matrix. I'll call it M tilde. So my matrix is going to have columns corresponding to the regions and rows corresponding to the vertices. And of course, we're just going to transcribe these. So I have TA minus TC plus E minus b, and 0 if nothing appears there. TA minus TB plus E minus D and a 0, and TA minus TB and an E and a minus 1 for C and a 0. Now you will notice that the columns are dependent. You add up all the columns, you add up all the columns, you get 0. And furthermore, we're looking for a determinant. That's our strategy. And we also know that regions is equal to nodes plus 2 for connected knot diagrams by Euler. And so what we're going to do, what Alexander tells us to do, and then shows that it's well defined, is we're going to strike two columns that correspond to adjacent regions. So for fun, let's strike this column and this one. That's A and C. So I struck this column and that one. Now I have exactly as many regions as I have columns, and I have a 3 by 3 determinant. And I'll call the resulting matrix M. And then the definition of the Alexander polynomial is delta K of T is equal dot determinant of M. Equal dot means equal up to plus or minus T to the N factor. You're allowed to multiply by plus or minus T to the N. That's the level of well-definedness of the Alexander polynomial. So we want the determinant of M. So let's see, what's the determinant of M? The determinant of M is equal to the determinant of minus 1, 0, 1, minus T, minus 1, 1, 0, minus T, and 1. If I got it right. And that's equal to, let's see, minus the minor, minus 1, 1, minus T, 1, plus minus the minor, minus T, minus 1, 0, minus T. So that's equal to minus 1 plus T minus T squared, and that's it. So this is equal to 1 minus T minus T, let's see, 1 minus T squared. There's a sign error here. Let's find it. Plus, minus, plus. This should have been plus. There we go. So that's equal to T squared minus T plus 1. The Alexander polynomial of the trefoil knot is equal to T squared minus T plus 1. Okay? So that's Alexander algorithm for the Alexander polynomial. Now, what we're going to think about now is making more combinatorial the terms in this determinant. What are the terms in this determinant? Consider a term in the determinant. And I will, with the help of a little extra, no, let me keep it black. Let me draw the underlying diagram again. Over here. Let's see. Let's move these equations a little bit to the left. Now, let me draw that diagram again. Now let me take a term in the determinant. Let's use blue. Now a term in the determinant is a triple choice in the matrix. Like it could be this choice, which corresponds to this choice here, where every element occupies one row and one column individually, right? And how do you say that combinatorially? You can say that B chooses 1, D chooses 2, and E chooses 3. Choice like that, where the choices are unique for each region. So now I'm trying to speak the language of regions. So the region chooses the vertex. And we have the vertices. They are 1, 2, and 3. And we have B making a choice. And B chooses 1. And I will denote that like this. B chooses 1. D chooses 2. And E chooses 3. You now see that the terms in the determinant are, we removed 2, remember we removed 2 regions. Alexander, of course, in his paper does the linear algebra. He doesn't go into this kind of combinatorics. He does the linear algebra and proves that it doesn't matter which 2 columns you struck. That has to do with the fact that these are dependent. And you'll get the same polynomial up to equals dot. And then he goes on to prove that it's invariant under the Rademacher-Briggs, Alexander-Rademacher-Briggs moves. But we now know that the determinant that we're after is a sum over contributions from these markings of the diagram. And the markings consist in every region chooses one vertex out of that region and marks it. And so you see in every region exactly 1 marker and no markers in the 2 regions that have been deleted. Furthermore, that marker is touching the algebra bit that was involved. You see, this is the algebra bit that was involved. But how can we understand the algebra bit that was involved? Well, let's take another slide. We can get rid of the matrix in some sense now and just talk about it. Oops. Maybe I don't want to get rid of everything. Let's be more circumspect about that. Let's just get rid of this. All right, now we have a little room. Let's do another one, another term from the determinant. I'll use green. Let's take a different term from the determinant. Say we take this one, this, and that. Now, in that case, B chose 2. and D chose 3. And E chose 1. You see, another one. Now, I want to illustrate the algebra bits this way because you see, if you have a crossing, then you know what the algebra bits are. They are T, minus T, 1, and minus 1, right? That's what you will see at a crossing. So when you see this in the diagram, then the algebra bits are T, minus T, 1, and minus 1, right? Didn't even need to know the orientation of this line. It's just the undercrossing line in doing Alexander. So we have that this must cover an algebra bit. So I will put the orientations in to make it easier to make the comparison with the diagram. But then we can look back up here and ask, well, what algebra bit does this correspond to? T minus T, 1. What algebra bit does this correspond to? T minus T. Okay. And what algebra bit did this correspond to? Well, it is T minus T. And as you see, those are there they are, minus T, and 1. But you no longer need the matrix. You can go directly from the knot diagram and this marker state to the term in the determinant. The term in the determinant is the product of the algebra bits covered by the markers. So we can write the following, that the Alexander polynomial in T is equal to the sum over S, a marker state, product of algebra bits marked by markers. And then we have to say one more thing, times the sign of the state. And by the sign of the state, I mean the sign of S's permutation. Because you see, there's a permutation. The one we had originally is the identity permutation. B chooses 1, D chooses 1, E chooses 1. By default, that's the identity permutation. But then this one is a different permutation. And when you do determinants, you reorder the rows and get the sign of the permutation, or you think of the sign of the corresponding permutation. And the determinant is given by the product of the matrix elements times the sign of the permutation, but now it's just the sign of the state. But we're going to find, remarkably, that the sign of the state, that permutation, which could just compute, is actually also implicit in the combinatorics of the marker states. But this is the Alexander polynomial now, and we see that the Alexander polynomial is the sum over these states of marker placements in the diagram like that. So let me go on and simplify it a little bit further. So I'm just going to state this one. It turns out that the sign of the state can be replaced by -1 to the number of markers that go inward. So I used to say -1 to the number of black holes in the state, where a black hole is where it goes in. And of course, the other one would be a white hole going out. And these two marker states would be neither black holes nor white holes. And there seems to be a pun here about the Penrose diagram for a black hole white hole pair, or an Einstein-Rosen bridge, which maybe we ought to explore further, but that's what it turns out to be. So now what do we have? Now we have that the Alexander polynomial in T is equal to the sum over S belonging to marker states Ks -1 to the number of black holes. And the Ks is equal to the product of algebra bits. And we can figure out what the algebra bits are. Let's just do it in the usual sort of crossing notation, crossing positive, crossing negative, so we can see what it would be for Alexander. So for Alexander, these are the dots in the positive crossing, and these are the dots in the negative crossing. So you can read them from that. The algebra bits are T minus T, 1 minus 1, and T minus T, 1 and -1. And then this will hand you the classical Alexander polynomial as a state sum. And the definition is now entirely in terms of the markers. So we ought to see it happen here for the truffle knot. Let's do it over here and get the same result that we had before. So here's a truffle knot. And we need 3 states. There are 3 states, I mean. There are 3 states. Here's one. Here's another. And here's a third. And now we can get the contributions to these. But if I want to amalgamate these two together, well, then I can keep track of where my black holes and white holes are. So I can do all of that. Let's write down the algebra bit here. What's the algebra bit here? -1. What's the algebra bit here? T plus, minus, plus, minus. Algebra bit of -1 there. And what about here? Plus, minus, plus. Okay. And what about this one? This one is the same as before, a -1. And this one is plus, minus, plus. And this one is plus, minus t. And this one has a t minus t. And t minus t, 1 minus 1, 1. And this one is a t. Sorry, t minus t. Now, we saw all these before, and if I got my signs right, I can simplify a little further, and I will, but let's just do this because we were doing Alexander. Then we add these up with their signs. Now, what about the sign? That's a white hole, that's a white hole. This one is totally a plus sign. This one here, white hole, black hole, right? So that one's a minus. And this one, black hole, black hole. Two black holes make none, so this is a plus. So now we can add it all up. And we get 1 from that one, minus, minus. Then we get the product of these, and we get a minus, minus t, minus t. We get a minus t. And from this one, we get t squared. And there it is again. T squared minus t plus 1 is the Alexander polynomial of the knot. But now calculated by a state sum over the states of the crossings. Now I want to go one step further, and then we can lift our heads up from this a little bit. But let me go one step further. We can get the Conway Alexander polynomial. Just by changing the weights, the algebra bits. And they're easier to remember and more symmetrical. For a positive crossing, we're going to use S minus S inverse, 1 and 1. And for a negative crossing, we're going to use S inverse minus S, 1 and 1. S bar equals 1 over S. And these minus signs take care of minus 1 to the number of black holes. Okay, so then the Conway polynomial in S, or Z, is equal to the sum over all the states of the product of marker touched algebra bits, and we've absorbed this. This is absorbed in KS now. Okay, so that's a nice normalization of the whole thing. And then you will find that for classical knots, nabla plus, nabla of a diagram with plus minus nabla of a diagram with a minus is equal to Z, S minus S inverse, nabla of a diagram with a smoothing. And you'll have nabla of 0 is equal, nabla of an unknown is equal to 1, and it's normalized, and it's invariant under all Rademeister moves. So the Conway version normalizes it, and we don't have to have equals dot anymore. And we have this very pretty state summation for the Alexander Conway polynomial. You might ask whether there would be a way to generalize this to get the Humphrey polynomial, but there isn't an obvious way that I know of. Recently, and I started to talk to you about that last week, Nestle Hahn and I realized that we could generalize the state sum and get a very interesting invariance of knothoids. In the interest of time today, I won't go back and talk about that, but I want to go forward now and talk about how these states end up being related to the knot floor homology and what kind of problems that gives rise to. Now, we are again going to be skirting the subject of knot homology, Floer knot homology, without quite really going into it in detail, but you'll get a flavor of it. And then we can state the problem, which is the problem that we're going to run into is the following. I can state the problem right now. The marker states give rise to the Conway polynomial. So you might ask, being such sophisticated persons about categorification, perhaps there's a complex related to the marker states that leads to a categorification of the Conway polynomial or the Alexander polynomial. And the answer to this question is yes. And this is what Oswald and Szabo did. But they did, and they did it by a very sophisticated line of thought. And I'll show you a little bit about that in the last few minutes, and we'll talk more. But they did it by in their theory, the set of marker states generates, let's call it S, generates a chain complex and originally the boundary, taking the module generated by these states to itself. I'm not worrying about grading, remember. So homology is just a module with a mapping, or it's a square zero to itself, right? You can worry about the grading. Then that boundary mapping comes from high-dimensional topology, high-dimensional differential topology. And so then there is the question, a combinatorial version of boundary. And this is an unsolved problem at the moment, but it's a partially solved problem at the moment. There is a partial solution in what's called bordered Floer homology due to Oswald, etc. What they do is they have quite a bit of algebraic machinery, and they construct, using the states, these states that we've been talking about, a homology theory, but they, I believe, at the present time don't know if it's this homology theory, the original one. And furthermore, there's quite a lot of algebra. You might think there would be a naive way to look at our states, the ones we've been talking about, and see how to do it. And that's the question that I wanted to talk about. But I don't have a lot of time left today, so I want to tell you a little more about how this high dimensional thing comes in relation to this, just a little. And then we'll continue with this for the last time, talking about some speculations and ideas about this other theory in relation to these not combinatorial. Okay, so let me go to another slideshow for the sake of this. Sorry, no, not that one. Sorry, I have to get things out of the way to get to things. There it is. All right. So these are some slides in which I have some of those explanations, and you'll get these slides as well in my notes for this time. The slides contain a recollection of what I was just doing in time on Blackboard, and we don't need to look at it again. Except for one thing, and that is when we were looking at these states, if you take two markers that have a common region on either side of them, this is in one region and there's a common region on the other side, then you can shift the markers. You can transfer this marker to this region and that one to that one. And I call that an exchange move or a clocking move. I call it a clockwise move if the marker rotates clockwise when it turns by 90 degrees. You see, they will both rotate clockwise. And for example, this state has a clockwise move taking it to this state, and this state has a clockwise move taking it to this one. Oh, there is a clockwise, counterclockwise order to the rotations of these states. And this suggests an ideal for doing homology that's something like, but you'll have to flesh it out, and we will. Why not say that the boundary of this is equal to this? Because you can go from you can do a clocking move to get from here to here. And then perhaps the boundary of this one is that one. And the boundary would have to do with the clocking moves. It's an idea, but you need more work. So we have these clocking moves. So here is in the last few minutes, there's a little sketch of how the knot floor homology works. You start with a knot in the three sphere. And then you place the knot on a surface and think of that surface as a Haggard decomposition for the three manifold that is the three sphere. And let me go immediately to a picture so you see what I mean. Here is a knot, truffle knot, and I've put it on a surface. And I have done that in such a way that that the regions in the knot diagram correspond to these curves which bound in the outer part of the handle body, like that. And then meridional curves around here near the crossings bound inwardly to form the inner handle body. So the crossings correspond to meridional curves bounding inward, and the regions correspond to sort of longitudinal curves bounding outward. A Haggard diagram for a three manifold is described by a surface where you tell which curves bound in one handle body and which curves bound in the other handle body. So you can think of this picture as a picture of a Haggard decomposition of the three-dimensional sphere, with labeled bounding circles for the outer handle body and the inner handle body, and the knot is drawn in the surface, and you could choose a certain base point if you wanted to. So their prescription reads like that, but more generally, you choose a marked Heegard diagram, some surface of some genus. There are the attaching circles for one handle body, the attaching circles for the other handle body, and a marked point on one of these. And then it's given that when you put everything together, you get the three-sphere. And the knot is disjoint from the attaching circles and meets the beta 1 in a single intersection point. So then they do the following incredible thing. You wouldn't think of doing this unless you were in their long evolved way of thinking. They take that surface sigma, the Cartesian product of it with itself, G times, where G is the genus of the surface, and they divide out by the action of the symmetric group. So they take the symmetric G-fold product of the Heegard surface with itself. And inside of that is the equivalence class of the product, the G-fold product, that's a G-dimensional torus of the curves that go into one handle body. And there is the product of the curves that go into the other handle body. It's G-dimensional, but modded out by permutations. And then you look at the intersections between T alpha and T beta, these toruses, these high-dimensional toruses. And a point in one of them can be regarded as a sequence of points which are in the intersections of alpha i's and betas permuted by some permutation. But the permutation by the beta means that since we have regions and crossings for the alphas and the betas, it means that the beta corresponds to one of the corners of the region. It means that this corresponds to one of our states. So the intersection points of the T alpha and the T beta correspond to one of the marker states. So that's how the marker states end up going up to live in high-dimensional topology. And then with these symmetrized toruses, the generators for the chain complex are the intersection points between the T alpha and the T beta in the symmetric product, and they correspond to the marker states. And the differentials on that complex are defined in terms of the embeddings of holomorphic disks in this G-fold symmetric product. So now you're doing high-dimensional topology and thinking about how certain complex structures up there and disks can touch one another. And the differentials are defined in terms of that, and I won't go into that now. We'll quit now, but that's how it goes. And they define their homology theory like that. And because it touches down on the FKT states, it ends up categorifying, this homology theory ends up categorifying the Alexander polynomial once all is said and done. So you end up with a graded Euler characteristic. I'll skip the rest of this. You ended up with a graded Euler characteristic of their homology theory is the Alexander polynomial. And it's based on the marker states. So one would hope that there would be some really clean way of defining differentials on the marker states in such a way that this homology theory would descend directly. As you perhaps know, this gave them quite a lot of difficulty, and they gave up on it originally, and then they came back to it. But in giving up on it, they found a different way to do it by using a different choice of Heegard decomposition that uses the grid diagrams that you may have seen. And those grid diagrams then have combinatorics that elucidates different kinds of states for which you can make the chain complex. So from from this point of view of looking for the way the significant combinatorics is working in these theories. This is a beautiful problem, but involves quite a bit more study to be understood. And I wanted to kind of end the course with some talk about this, since it's related to combinatorics that I'm very interested in. And so next time I will tell you about at least one attempt to make a chain complex. It is known not to work perfectly, but it does give you a chain complex, just not topologically invariant. And of course, we want one that's topologically invariant. So I'll stop here.